People often think science is just a long list, separate, disconnected rules. One rule for why a ball falls, another for why the sun shines, a third for why a spinning top stays upright. It feels like there's no single grand idea holding it all together. This is a small, quiet myth. A myth that the universe is just a jumble of unrelated laws. But what if I told you that behind many of our most fundamental laws, the laws of energy, of motion, of spin, there hides one single, elegant, and profoundly simple concept? It's an idea discovered in 1915 by a mathematician whose name you should know, Noether. You see, the universe isn't just a collection of facts. It has a hidden architecture. Her idea, often called Noether's Theorem, is not loud. It doesn't shout from the headlines, but it is one of the most beautiful and powerful truths ever uncovered about our cosmos. It connects what we see with what we can't. It explains why some things in the universe must stay the same, no matter what. It's a bridge between the abstract world of mathematics and the physical reality we all experience. So, what is this magic idea of symmetry? It's simpler than you think. Symmetry just means a thing stays the same even after you do something to it. Think of a perfect sphere. You can rotate it any way you want, and it still looks like the exact same sphere. That's rotational symmetry. Or think of an endless, repeating pattern on a strip of wallpaper. You can slide it along its length, and the pattern doesn't change. That's translational symmetry. You've changed something. The orientation, the position, but the object itself appears unchanged. It has an underlying sameness. Now, let's take that idea and apply it to the laws of physics themselves. What if the fundamental rules of the universe had their own kind of symmetry? What if the laws that govern reality don't change when you move through time? This is called time shift symmetry. It means an experiment performed today will yield the same results if performed tomorrow, or a billion years from now, all else being equal. The cosmic rule book doesn't have different chapters for Monday and Tuesday. It's the same book, always. Noether's theorem makes a startling connection. Let's look at 3 classic examples. They show just how powerful this one idea is. First, as we just saw, is the symmetry of time. The laws of physics are the same today as they were yesterday, and as they will be tomorrow. An electron behaves like an electron. Gravity pulls the same way. Because of this unwavering consistency through time, there is a quantity that must be conserved. That quantity is energy. The total energy of an isolated system never changes. It can transform from chemical to kinetic to thermal, but the total amount is always the same. This is why a perpetual motion machine is impossible. It would violate the universe's indifference to the calendar. Second, consider the symmetry of space. The laws of physics are the same here as they are over there. The rules don't change if you move your experiment from New York to Neptune. This is called translational symmetry, sameness under a shift in location. Because the universe doesn't have a special preferred spot, Noether's theorem demands that another quantity must be conserved. That quantity is momentum. It's the oomph of a moving object. An object in motion stays in motion unless an external force acts on it. This fundamental law of motion is a direct result of space being the same everywhere. How does this actually work? How do physicists go from a symmetry to a conserved quantity without just waving their hands? Imagine a physicist's rulebook for how something moves. This rulebook is a mathematical recipe called the Lagrangian. It basically describes the energy of a system in motion. To predict the path of a planet or a particle, you find the one path that minimizes a special total value called the action, calculated from this rulebook. It's nature's way of being efficient. It always follows the path of least action. Now, Noether asked a clever question. What happens if you tweak the system a little bit? For example, what if you shift everything forward in time by a tiny amount? If the system has time symmetry, the laws don't change. This means the rulebook, the Lagrangian, also doesn't really change in a meaningful way. When she worked through the math, she found that this invariance, this sameness under the tweak, forces a certain mathematical expression to always be zero. This expression, in turn, reveals a quantity that must remain constant over time. That constant is the conserved quantity. You don't need to see the equations to get the picture. The core idea is a bit like a detective story. The symmetry is the clue. The Lagrangian is the scene of the crime. By examining how the scene stays the same even when a small change is introduced, the detective, the physicist, can deduce something that must be true.